Hello guys and welcome to today's video. Now we are going to learn how to find the Laplace transform of finite time domain signals. So when I say finite time domain signals, I mean signals that are not defined across all time interval from 0 to infinity. So these are what I call piecewise signals. So they are just defined in a certain portion of infinity. Like you can see that this ramp function or this sawtooth function is just defined from all time from 0 to 1. So it is not defined from all time from 1 down to infinity. So it is a finite time domain signal. Okay, so we call it the sawtooth signal. So how do you find the Laplace transform of this kind of signal? So watch with me as we delve to the simple process of finding the Laplace transform of this signal. So solution. So first things first is that you need to define your signal. So using the Heaviside patterns of defining signal or using branched function pattern. So using this graph of x of t or this sawtooth function, I'll define what is happening in this particular function. Okay, so I'll define it in this way. And my x of t is a branched function. Okay, it's a branch function. So it has two particular behaviors. From the interval of time from 0 to 1, my x of t is a ramp function. Okay, it's a ramp function. So a ramp function is a function whereby let me just demonstrate it. It's a ramp function like this. So y is equal to t. So this is your y and this is your t. So it's a function that returns an image of the input that you give to it. So if you give it an input of 1, it returns you 1. If you give it an input of 2, it returns 2 on the output. If you give it an input of 3, it returns 3 on the output. So generally, y of t is equal to t. So that's the definition of a ramp function. So that is why in this place they wrote 1, 1. Okay, so the slope is 1. Therefore, if you're writing this function in the straight line pattern, you just write it as y is equal to, or in this case, x of t is equal to slope, which is 1, then t plus your intercept, which is 0. In other words, x of t is equal to t. Okay, so x of t is equal to t is the general definition of a ramp or a sawtooth. Okay, so you need to take note of that. So x of t equal to t is the general definition. So the function behaves in two ways. From 0 to 1, the function is a ramp function. As you can see, from 0 to 1, it is a ramp function. So defining x of t, I'll have t. Okay, the value of x of t is t for values of t between 0 and 1. Now, for values of t, okay, that is greater than 1, you can see that the value of the function is now on 0. So the value of the function is on 0. Nothing was defined. So for values of t greater than 1, this function is 0. Okay, so the value of the function is 0 for t greater than 1. So this is the behavior of this sawtooth function. Now that you have identified the behavior of this sawtooth function, okay, you can now find the Laplace transform. So the Laplace transform of x of t is going to be integral from 0 to infinity x of t then exponential minus st dt. I hope we all remember the Laplace transform of an f of t, which is the integral from 0 to infinity f of t exponential minus st dt. And this translates to capital letter F of s. Okay, so that is what is going to happen in this case. So this will translate to some x of s. Okay, so now the problem with this definition is that we must make sure that we break our intervals. We must break the limit of our intervals according to the breaks that we have in our function. Like for instance, our interval is in such a way that from 0 to 1, the function behaves in one particular way. Then from 1 to infinity, or for t greater than 1, the function behaves in another way. So this is how I'm going to break this integral. So the Laplace transform of x of t is a capital letter X of s, and this is going to be integral. So the first behavior starts from 0 to 1, and in that behavior we have a particular x of t. I'll just write it like this: exponential minus st dt, then plus. Now you can see that from 1 to infinity there is a particular x of t, exponential minus st dt. Okay, so you can actually write this like this. Okay, so it's still the same thing. All we know is our integral starts from 0 and it ends at infinity. So there can be any number of breaks. So it must start from 0 and must end at infinity. So this is exactly the same as this. Okay, so 0 to 1, then 1 to infinity is still the same. Now, you can now write your x of s as the integral from 0 to 1. So what is x of t between the intervals 0 and 1? As you can see, x of t is given to us as t. So you now write your t dot exponential minus st dt, then plus integral from 1 to infinity. So what is x of t between 1 and infinity? So for t greater than 1, which is still the same thing as 1 less than t less than infinity. Okay, t greater than 1 is the same thing as 1 less than t less than infinity. You can see that the value of x of t is 0. So at this point, you write 0 dot exponential minus st dt. Now, the beauty of this integration is that this part will be 0 because of this 0 here. So you just have to focus on finding the value of this part. So our x of s is now going to be the integral from 0 to 1 t exponential minus st dt. So at this point, I'll borrow knowledge from reduction formulas. So I'm going to say let I1 be the integral from 0 to 1 t exponential minus st dt. Okay, so I'm borrowing knowledge from reduction formulas. So from reduction formulas, in is given as the integral from 0 to or let me just put it like this. Let me not put any limits. In is the integral of t raised to the power of n exponential at dt, and in evaluates to t raised to the power of n exponential at all over what? A minus n over a I n minus 1. If you're not conversant with how I got this particular reduction formula, you should watch the video just before this one on reduction formulas for Laplace transform, and you will understand how I got this particular formula. Now, this reduction formula, with this reduction formula, I also establish that I naught, that's the I0 is exponential at over a. So we should take note of the application of these two. So that's what I want to use to solve this one quickly. So my I1 is going to be what? The integral from 0 to 1 t exponential minus st dt. So I'm going to apply the reduction formula like this so that you will see how we're going to get something out of it. So my I1 is going to be, according to this formula, you're going to take n as 1. Okay, anywhere you see n, you're going to put 1 there. So I'll have t raised to the power of 1 exponential a. Now your exponential a t, a is, in this case, is minus s. So anywhere we see a here, we replace it with minus s. So you now have minus s t. Okay, let me make sure shift it up again, all over minus s, then minus, look at it here, and you now have your n, which is 1, all over your a, which is what? Minus what? Very good, minus s, and you now have I n. in this case is 1, so 1 minus 1 is 0. So we established that our I1 is still the same thing as what? If you're following me, you have t raised to the power of 1 is t exponential minus s all over minus s. Then you now have minus 1 all over minus s. So recall that I naught is equal to exponential at over a. So in this case, all we just needed to do is to replace this I naught with exponential at over a. And remember, our a is acting as minus s. So you're going to have that exponential minus st all over minus s. So are we good? So the problem is that this is a definite integral. So immediately after you write the value of I naught, you need to enclose the whole of this in this square bracket and you take it from 0 to 1. Is that okay? So very good. So we'll now have our I1 is equal to the integral. So you can write this one as minus t, okay, exponential minus s over s, then minus times minus will give you plus, and you now have exponential minus st all over s times s is going to give you s square. Are we together? And you now have your 0 and 1. So at the end of the day, we just have to what? Apply this definite integral. So remember what our I1 was. Our I1 was referenced from x of s. So we can take it back to x of s. So my x of s is going to be equal to the definite integral of this particular stuff, which is when t is 1 minus when t is 0. So you now have minus 1 times exponential s is going to be 1 dot exponential minus s, sorry, all over s. And you now have exponential minus s times 1 and all over s square. Then you now subtract it from when t is 0. You now have minus 0 dot exponential minus s over s, then minus exponential minus s dot 0 all over s square. So note what is happening. So this term is going to cancel out, and anywhere we see exponential something times 0 is still the same thing as exponential 0, which is equal to 1. Okay, so take note of that. Exponential something times 0 is exponential 0, and exponential 0 is 1. So what we are going to have is your x of s is going to be arranging this one. Minus 1 times this is going to give you minus exponential minus s over s. Then you now have minus, if you simplify, you get exponential minus s times 1 is minus s over s square. And you now have your minus. Opening this bracket, you're going to get that this term cancels out. So you now have 0 minus. Then if you evaluate this, you have exponential 0, which is 1 all over s square. So at the end of the day, x of s is going to be, if you simplify, you have minus exponential minus s over s minus exponential minus s over s square, and minus times minus is plus 1 all over s square. So it's usually good to put the plus before the minus. So you have it as 1 all over s square and plus, sorry, 1 over s square, okay, which is the positive one. Then you now have minus exponential minus s over s minus exponential minus s over s square. So there's a common denominator, okay, which I see. So my x of s is the same thing. My common denominator is s square, but the problem is that this term does not have an s square. But how about I multiply the numerator and the denominator of this term by s? So I'll write it as 1 all over s square minus s exponential minus x all over s square. Okay, you multiply here and here by s square, and you now have minus exponential minus s over s square, and this will simplify to 1 over s square. In bracket you have 1, okay, you now have minus s exponential minus s, then you now have minus exponential minus s again. So we can actually simplify this further, sorry, This is what we got as our x of s. It can be written as 1 over s squared into 1 minus. Since exponential minus s is common, you can have exponential minus s into s plus 1 like this. So this is the frequency domain representation of the sawtooth function. So if you have this as your answer, you are correct. So I want you to take your time and go through this process, go through the reduction formula. It's very important for you to understand the reduction formula. Don't just cram it, but understand it very well so that you can apply it and get your answer and move on with your life. So I hope you understood this video. I hope you like this particular pattern of solving. And in the next video, I'll solve for another signal that will convert from the time domain to the frequency domain. So stay tuned and stay blessed. Bye.